All right, welcome back everybody. We are continuing the integrating using substitution. This is part 3 of our lessons on integrating using substitution for section 6.9 of AP Calculus. In this one we're going to handle some trickier substitutions, some things that I consider, more bizarre situations, and some of the harder kinds of problems that we can do using integration by substitution. So let's go ahead and we'll start with example 1 here. We're integrating the integral of x times the quantity x minus 2 to the 7th dx. And I mean, if I look at this, we talked way back early on when we were doing integration about how we had no, rule to integrate products of things. I mean, I could take x minus 2, that quantity to the 7th power, and expand it out, but I have absolutely no desire whatsoever to do anything remotely close to that. So I'm going to try and handle this via substitution. Now, we also know by now that when we're doing integration by substitution, the best first approach is looking for something that is, inside of another function. It's part of a composite. So I think most of us, if we were approached with this problem and we said, okay, let's try and do this by substitution, we'd try and use u equals x minus 2. Okay? So that's our u. That's going to be u to the 7th. And then if I take the derivative of this, I get du equals dx. And so that takes care of this portion. That's my dx. Unfortunately, I have an x left over here. And realistically, what's happening is, if I use these two pieces to make the substitution, this becomes the integral of x times u to the 7th du. Of course, in order for me to integrate this with respect to u, at this stage in the game, I need everything in my integrand to be in terms of the same variable. Okay? So if I'm going to integrate with respect to u, I've got to replace this x right here with an expression of u that it is equivalent to. And this is not as hard as it really might seem at times. We almost have the substitution staring us in the face right here. We want to replace x with what it's equal to in terms of u. So I'm going to take this expression right here, and I'm just going to add 2 to both sides. And that tells me that x is equal to u plus 2. And so this is equal to the integral of u plus 2 times u to the 7th du. Now, what is the advantage of this form of this integral instead of the original form? Well, very simply, I can distribute the u to the 7th through this set of parentheses, since this is a quantity raised to the first power, whereas I could not have distributed the x into these parentheses, since this is a quantity x minus 2 to the 7th power. And so I'm just going to go ahead and distribute the u to the 7th through here, and that turns this into the integral of u to the 8th plus 2u to the 7th du. And now I can go ahead and find this integral using the antiderivatives. This is going to be u to the 9th over 9 plus 2u to the 8th over 8 plus c. Which is equal to, and u was the quantity x minus 2, so this is the quantity x minus 2 to the 9th over 9 plus the quantity x minus 2 to the 8th over 4 plus our constant. And there is the integral of x times the quantity x minus 2 to the 7th power. All right, and I could manipulate that into a different form. I could factor the quantity x minus 2 to the 8th out of both of the terms here if I felt like it. But since our focus in this lesson is substitution and not algebra, I'm just going to leave it at that. All right. Example 2. Goodness gracious, there are so many things that I could pick as a first substitution here to try. In general, in this example 2, when we have something this complicated, sometimes it's better for us, instead of trying to look for that absolute best substitution, it's best for us to just pick a smaller substitution, use that substitution, and then make another substitution and simplify more from there. So I think what I'm going to do in this one, instead of trying to work too hard for a substitution, I see this quantity 4x squared minus 5 a bunch. And I know that if I take the derivative of that, it's 8x minus 5, which is a factor of this 32x minus 20 right here. So I'm going to go ahead and start and just say, okay, let's let u be the quantity 4x squared minus 5x. And then we take the derivative of this, du is equal to the quantity 8x minus 5 dx. Okay, so looking at this, we've got all these that are going to be replaced by u. We've got this, which is going to be replaced with, let's see, that's negative 4 times du. There you go. That's negative 4 times du is going to replace the green highlights. And all of these are functions that have our u inside of them. So making that first substitution, u equals 4x squared minus 5x, turns this expression into negative 4 times u cosine squared of u squared sine of u squared du. Okay, so there's my first substitution. Now this is something that when I look at it, I can't just take the integral of this, using basic antiderivative rules. So I'm going to try and use substitution to simplify this a little bit more. I'm looking for something that's inside of another function. I see, hey, I've got a u squared that's inside of the cosine squared and inside of the sine. So let's let t be equal to u squared, in which case dt is equal to 2u du. Okay, and let's see, let me do my highlighting here. I've got t equals u squared, so there's a u squared, there's a u squared, inside of the cosine and the sine function. And what's left is negative 4u du. So I can get that if I just multiply this by negative 2. That's negative 4u du is equal to negative 2 dt. So I can replace, and this is now equal to negative 2 integral of cosine squared of t sine of t dt. At this point in time, it's important for me to remember that cosine squared means cosine of t quantity squared, because I'm going to do one last substitution. What letter should I use? Let's use, I don't like to use the letter S. Let's use the letter R. So let's let R be equal to the cosine of t, and then dr is equal to negative sine of t dt. So looking at what I've got going on here, this is my R. Everything that's left is negative 2 sine of t dt. So that means I can just replace that with a negative 2 dr, or pardon me, a positive 2 dr. It's going to be negative 2 sine of t dt. And so this is going to be equal to 2 times the integral of r squared dr. And now that is something that I can integrate using antiderivatives. That's going to be 2 times r to the third over 3. And there's my integral. And now I just need to bring my variables back. I'm going to bring r back. It's going to make this 2 cosine cubed of t over 3 plus a constant. And then I've got to bring t back. T is equal to u squared. So this is 2 cosine cubed of u squared over 3 plus a constant. And then I've got to bring u back. So that's going to be 2/3 cosine cubed of the quantity 4x squared minus 5x quantity squared plus c. And there is our integral. of the original. All right, that was fun. Let's go ahead and move on to example 3. All right, example 3, integrate the integral 10x plus 3 over x squared plus 16. Okay, this one, I'd like to use x squared plus 16 as a substitution, but x squared plus 16, the derivative of that is 2x dx. So I can't really, with the 10x plus 3, the key here in this one is there are times when I have multiple terms in the numerator that it is to my benefit to split this into two integrals and make this the integral of 10x over x squared plus 16 plus the integral of 3 over x squared plus 16. And now that I have those two separate integrals, I'm going to use two different substitutions. For the first one, I'm going to use u equals x squared plus 16, which makes du equal to 2x dx, and so 5 du is equal to 10x dx. So this first integral turns into the integral of 5 du over u. So that's not too bad. For the second one, I recognize that this is an inverse tangent kind of format. I would like this to be, u squared plus 1. So I'm going to try and turn this into u squared plus 1. And the way I do that is I make this x squared have the same coefficient as the constant here. So I'm going to make the substitution. I'm going to replace, actually I already used u in this problem. I'm going to replace x squared with 16t squared. And then that means x is equal to 4t, so dx is equal to 4 dt. So using this substitution turns this integral into the integral of, replacing the dx with 4 dt makes it 12 dt, replacing x squared with 16t squared makes it look like this. And then what I can do is I can factor out of the numerator and denominator. I can factor out a 12 out of the numerator and a 16 out of the denominator. 12 over 16 is 3/4, and this becomes the integral of dt over t squared plus 1. And now I can take the antiderivative of each of these individually. This is going to be 5 natural log of the absolute value of u plus 3/4 arctangent of t plus a constant. And then I need to bring my variables back. And this is going to be equal to 5 natural log of x squared plus 16 is always positive, so I don't need the absolute value signs there in my natural log. Plus 3/4 arctangent of, and t, since x is 4t, that means t is equal to x over 4. And there's my integral for that one. Pretty tricky one right there. All right, we're going to come back. That's about all the time we have for this video. We're going to come back and do a second video to finish up the examples from this lesson. All right, we will go ahead and see you next time. Have a great rest of your day and enjoy yourself.